giggling. Oh my goodness, I wish my classes would fall so quiet so quickly. That's amazing. Good evening, everyone. My name is Janet Hurt. I'm Deputy Dean of Science here at the University of Melbourne, and it's my very great pleasure to welcome you here on a very, very cold wintry night. So well done for coming out in the cold and dark tonight. I want to welcome you to the first of this year's July series of lectures in physics. I'm reliably informed by people in the audience that have been coming for a very long time, and also our speaker tonight, that these have been running since 1968. That's just so amazing. They comprise 4 lectures each year on fundamental issues in physics, and as you can see from the slide behind me, this year the theme is Important Applications of Physics in the 21st Century. It just so happens that this year is also the year of crystallography, so the second presentation you can see on the board there will combine these 2 themes, so I hope you come along to the next one as well. Tonight's lecture, however, is presented by Professor David Jamieson. David's a Professor of Physics here at the University of Melbourne, and in fact he was a PhD student here at the University of Melbourne many, many years ago. Perhaps not so many, but I'm sure he attended many of these series at that time. He then went on to work at Caltech in the USA and Oxford in the UK as a postdoctoral research fellow, and most recently he's spent 6 years heading up the School of Physics here at Melbourne from 2008 to 2013. His research expertise is in the field of ion beam physics, and he's a Chief Investigator and Program Manager in the Australian Research Centre of Excellence for Quantum Computation and Communication Technology. It's a bit of a mouthful, but it sounds really fascinating. David is a Fellow of the Australian Institute of Physics and served as its President from 2005 to 2006. He's also a Fellow of the Institute of Physics in the UK. From 2010 to 2012, he convened a national working group to develop the decadal plan for physics for Australia for the Academy of Science, and in 2013 he received an Outstanding Service to Physics Award from the Australian Institute of Physics. So he's kind of been there and done that, really, hasn't he? For those of you who haven't come across David before, you will very soon realise he's a very passionate man when he stands up here to speak. He's therefore a fabulous teacher, and the students love him. So he's an accomplished physicist, he's a great teacher, and I dare to class him as a good friend. It is therefore my immense pleasure to hand the podium over to Professor David Jamieson to deliver his presentation entitled Entropy, Energy and Climate Change. Thank you, David.
Well, Janet, thank you very much for that very kind introduction. For those of you who just came in the last minute, if you want to participate in this lecture, please point your smartphone at the web address on the screen, and further instructions will be provided shortly. It's a great pleasure to have such a good audience on such a freezing cold night to hear my lecture here on the topic of physics, energy, entropy and climate change. This is a lecture that I've given around Australia on numerous occasions, and it's interesting the aftermath from people who were either outraged, entertained or enlightened, often all in the same person afterwards. So let me give you my personal take on these important topics for the 21st century. I should also say that on a personal note, it's now 25 years since I gave my first July lecture in this series. I was not present at the first one in 1968, but my first lecture was given in 1990, and it's a pleasing series of lectures from my point of view because of the enthusiastic audience. So thank you again for those of you who have been to many of these perhaps in the past. It's the audience that makes this job worthwhile, whether in the public lectures in this forum or of course in the lecture theatres in my day job. So let me begin. Why am I doing this? Professor Ross Garnaut said that universities should have a formal role in developing the low emissions technologies of the future and training the interdisciplinary professionals required to help the country. So, okay, I'm happy to do that. A previous science minister, in fact, we don't have a science minister at the moment, but when we did, Kim Carr, great friend of science, said scientists should speak out more strongly against quackery in the climate change debate. I'm happy to do that. In conversing with a senior colleague at the university, a senior administrator actually, he commented that many of your colleagues don't agree with your conclusions, so I'll just keep trying then. Also, we have a remarkable asymmetry in our university with the introduction of breadth subjects, where you take subjects outside of your discipline. Science students have taken up art subjects with a great passion and enthusiasm. Sadly, the reverse has not been true. At some universities, like Harvard, for example, a science subject is a compulsory part of the curriculum for all students, and I have great sympathy for that. Also, we had a lecture by Eric Mazur, professor of physics from that same institution, Harvard, who said the plural of anecdote is not data. So this lecture tonight, I want to make largely about data. I was also motivated to give this lecture on a recent flight. I spend a lot of my career flying, so it often gives me an opportunity for deep thinking. Looking out the window on my return from Sydney the other day, I could see in the foreground a gigantic hydrocarbon-powered jet aircraft engine. I could see in the middle distance the snow on the Victorian Alps, not so much. And in the far distance, I could see steam rising from the cooling towers of the coal-fired power stations in the Latrobe Valley. And these three things are shaping our future. Now, it's remarkable that I am the only one sitting in this aircraft looking out the window. I guess everyone's looking at the movies or checking their smartphones or reading the in-flight magazine. But there's a lot of people that you don't see in this picture. And those people, even though we don't know their names and they live very far away from us, are nevertheless united with us and are part of the consequences of what we do, because we're all united, all of humanity are united by the tenuous gases of our atmosphere. What we in Australia put into the atmosphere has an impact on people all around the world. That worries me a great deal. And it has worried me for as long as I can remember. And here is an authentic image from my archives. The very first lectures I gave as a junior lecturer at the University of Melbourne back in 1990. I had the duty of lecturing to the first years. And back in 1990, I had to talk about where we get our electricity from. And I found this graph in Scientific American showing the carbon dioxide level in blue and the temperature difference compared to the present, as it was in 1990, in red. And it was a remarkable bit of data that the carbon dioxide and the temperature followed each other so closely. And also, if you expand, this goes back 160 years, and if you expanded just the last 10 years, from 1990, you could see the gradual rise of the CO2 ever steepening and the consequent rise in temperature. That I put up in conjunction with this image, which shows Africa seen from space. I'm afraid the graphics weren't so great in 1990. Black and white transparencies were the best we could have. But this shows the onset of spring vegetation across Africa, and everything above that green line is basically desert. That's in a normal wet season. Down here is the advance in the spring vegetation in a dry season. We now know that this line, the position of this line, is determined by the temperature of the Indian Ocean. And what worried me and what motivated me to put this up is that if I drop that green line down and superimpose it on on the dry year, there's a huge gap. And there's a lot of people who live in that gap, and who are wondering why it's so dry and why their crops are failing, and it's causing a lot of hardship. And there's been a lot of stuff in the news about that over the past decade. And so I thought, well, those people who live in that gap are not responsible for this rise in CO2, which is correlated in some way with the temperature. More on that later. And back in 1990, The amount of carbon dioxide in the atmosphere was 391 parts per million. We'll come back to that later on. Also, I thought it was worth pointing out that since this is my 25th year as a participant in the July lecture program, I should reflect back on the number of undergraduate students who have passed through my lectures in 25 years. So I added up roughly how many students I get to speak to each year, and this is the cumulative total from 1989 up until a couple of years ago, and I reckon it adds up to somewhere just over 5,000 precious young minds have passed through my lectures. But then last year it went to 45,000 because I participated in a massively open online course, and I presented a longer version of tonight's lecture over 18 15-minute segments to this audience. And it was remarkable to get the responses in the blogs after each lecture from people all over the world. The people from Yemen were complaining about this concept of rubbish because when they were growing up, the word did not exist in their language because they threw nothing away. The people in Mexico City were sniping at the inhabitants of Los Angeles, whinging about smog in Los Angeles. You want to see smog? Come to Mexico City. And it was just an amazing melting pot of people from all over the world with their opinions on the merits or otherwise of my lectures, and also interacting with each other. Made possible, of course, by the internet. I could not, using conventional technology, have reached such a large audience with my lectures, but the internet has suddenly made this possible. It's a remarkable tool. Who knows where this will go in the future? So anyway, let me now start with the introduction. We are surrounded by Western civilization. We take for granted the ability to fly, to turn the lights on, to connect to the internet, to light up our cities at night, and we can afford to do so. But I don't think we look at this one. We don't look very carefully about the future. How are we going to continue doing all this into the future without taking the planet down? So just to be clear, let me tell you where I am coming from, in case there's any confusion. First of all, I have access to electricity and all its benefits, 24 hours a day, 7 days a week, and the cost, I have to update that, the cost has skyrocketed. Okay, less than 50 cents a kilowatt hour. But only 20% of humanity has access to electricity. About 2.5 billion people depend on burning dung or wood or something for cooking fires, with a consequent enormous impact on health. And in some countries where the only access to electricity is by batteries because there's no grid, they're paying $330 per kilowatt hour, not 50 cents a kilowatt hour. That severely constrains what you can do. I think the people on this side should share in the benefits on that side. Furthermore, I have access to the means of travel, local, in my car, globally, in aircraft, to live, to work, to seek education, even to entertain myself. And it's safe and convenient. On the right-hand side, we can see that only about 3.2 billion passengers, only, were carried by air annually, and many of those were me, making multiple trips, by the way. So only a small fraction of humanity, maybe a third, actually ever flies. We only have about 1 billion cars in the world, yet there are 7 billion people. Is that the right ratio? I think the people who are missing out should enjoy that as much as I do. And finally, of course, the big one, access to information. Two-way, 24 hours a day, 7 days a week, the World Wide Web is on tap. The sum total of human knowledge and more besides. And I have a personal portal, I can tap it at any time. But only 32% of humanity has access to the internet because, you know, they either don't have electricity or there's no signal. Facebook has only about 1.3 billion users. Okay, I'm not in a hurry to wind that up to 7.2 billion actually. And there are only about 2 billion computers in the world. That's about 1 computer for every 3 people. I personally own 6, I don't know. So again, I think the people who are missing out on this side should have access on that side. The point I'm making here is that if we're going to be democratic about the benefits that we take for granted in our lifestyles for the people who don't have them or don't have the option of using them, then we're going to need an enormous amount of power. If we're going to roll out the internet, broadband, to 1/3 of humanity, it would consume half of the total electricity generating capacity in the world today. Maybe we shouldn't do that. Maybe we should keep everything on the left just to ourselves and not try and share it with our brothers and sisters around the world. So even though only a small fraction enjoy the things on the left in where I'm coming from, this is the footprint we have on our planet. And I haven't got time to talk about all of these wedges, most of which are greater than what the Earth can sustain anyway. The only one I'm going to talk about in tonight's lecture is the carbon footprint, which is already 2 or 3 times the sustainable level, even though it's only servicing a small fraction of humanity. So, thinking about our own country and where we're going, we would like to continue to, well, I would like to continue to enjoy the benefits on the left of my diagram without inflicting the consequences on the people on the right who don't have access to them or are gradually getting access to them. So this gives me the opportunity to set some targets for our country and what we should be doing about our own emissions into the atmosphere. But I'm not going to set these targets myself. I'm just going to take them from the literature. What should Australia be doing about reducing its greenhouse emissions? Well, the Intergovernmental Panel on Climate Change says that we should be cutting by between 20 and 30% by 2020, but 90% or greater by 2050. 90%! That means we have to turn off every power station in Australia, basically, and replace them with something else that doesn't emit carbon. The Garneau report from 2008, with its more recent update, said if we're going to stabilise the planet at 450 parts per million of carbon dioxide, a dangerously high level, then Australia would need to cut by 90% by 2050. Even if we take the more relaxed target of 550 parts per million, I call that the Armageddon scenario, it still requires an 80% cut by 2050. These are very challenging targets on a very short timescale. And the Green Party in 2010, I can't find this website anymore, they seem to have taken it down, but their manifesto for the election that year was that we should cut by 110% by 2050. In other words, not only should we reduce our emissions to zero, we should take steps to start removing carbon dioxide from the atmosphere and try and return the planet to pre-industrial levels. All of these are numbers we've got to worry about, and that's part of the purpose of tonight's lecture. So here's the framework I'm going to go through. We need to think about how much power we're going to need to run our country in the year 2050, the year where all of these organisations have set our targets. We should decide on how much carbon dioxide is safe in the atmosphere of the planet. Garneau thought we could do 450. The Greens want us to go back pre-industrial, say 270. What are the alternatives that we could roll out in time to achieve that target of 2050? There are not that many options. And finally, how much is that electricity going to cost? Because it is indeed electricity that produces most of the emissions from our country. The Brotherhood of St Lawrence has already set the pain threshold for electricity at like 27 cents per kilowatt hour, where they then have to deal with the people who can't afford to pay their bills. And this is a deadline fast approaching. So in order to answer all those questions and set the timeline, we're going to need some physics. Now I emphasise in a 50-minute lecture like this, I can barely get away from the fact that the world is flat and is actually round. And so the world isn't round either, it's actually pear-shaped. That's not a metaphor. But it's saying that the Earth is round is good enough for the first approximation, and it's a hell of a lot better than saying the Earth is flat anyway. So there's a lot of higher order considerations that there aren't time for. We're just doing the perfectly spherical approximation right now. Now I want to introduce you to the 3 laws of thermodynamics. At this point, most of the audience goes to sleep. Law number 1, actually it's the 0th law. We start at 0 for historical reasons. Heat does not flow between objects at the same temperature. Well, duh. 2, energy is conserved. And 3, entropy always increases. Now, that was the first question on this year's thermodynamics exam for my second year students. And only about 80% of the class got them right. That's a bit embarrassing. There were some very strange extra laws that I don't think have yet been subject to experimental test. But anyway, and as a hint, next year the same question will appear as the first question on the exam. What are the 3 laws of thermodynamics? And I'll keep it up until everybody gets them right. But these concepts, energy, heat and entropy, are not everyday concepts that the average person deals with. But there's another concept in our society that we deal with every day and we're really good at dealing with, which is exactly analogous. Let me tell you what it is. The laws of money. Here are the 3 laws of money. Law number 1, 2 things with the same price cost the same amount of money. Well, duh. You can only spend what you earn. Well, until the bank calls the loan in. And finally, you have to work hard to scrape the money out of the local economy into your pocket. It doesn't just come for free. You have to spend money to make money. That's entropy. More on that in a moment. So let me introduce energy because dollars are familiar, but joules are not. So here is a one-to-one analogy between money. The dollar comes from the German Thaler, from the place where silver was mined in Bohemia, and the silver coins were nicknamed thalers and later became dollars in English. The joule is the unit of energy, exactly analogous to the dollar, named after James Joule, who introduced the concept, and the joule is the metric unit of energy. And so these are things that we're used to thinking about as different forms of money, and these are things we think about as different forms of energy, batteries, petrol, gas, or power stations. There's a one-to-one analogy between joules and dollars. And just as a point of comparison, your heartbeat dissipates about 1 joule per beat, which is not very much actually. The human body dissipates about 60 joules per second as it operates, most of which from the brain. Now, let me just check to see how familiar everybody is with the value of $1. Let me ask now for you to turn to your mobile phones and participate in this first question. Please look at the options. Look at the options. And here's my phone. Please give me a rough guess at how much this phone cost me to buy. It's a Nexus 5, the latest Android running KitKat, of course. Fully loaded with apps. How much do you reckon I paid for that? Ooh. Okay, so we've got 49 people voting, 50 people voting. Okay, so that we don't go on for too long. Okay, so here's the result. The majority voted for A, $500, and they will be exactly right. That is indeed how much I paid for my phone. Very good. You clearly understand the value of an object and you know you can put a price on it. And this is true across our whole society. Even people who are not, pretend not to be numerate, prefer the bigger picture things, nevertheless know the value of $1. Here's a more difficult one. What about the value of a car, a new Ford Falcon? How much do you reckon one of those cost? Please hit the buttons and give me an opinion. Cool. Wow. Okay, so everybody's obviously just bought a Ford Falcon before they came to the lecture. And they've all got that absolutely spot on. If anyone knows where they can get one for $20,000, please see me afterwards. Thank you. All right, so clearly everybody understands the value of $1 and could put a price on things and get it pretty right. So now let me introduce the next concept, power. Because it's true that our civilization does not run on energy. Our civilization runs on power. In other words, energy delivered at a prodigious rate. Here's what I mean. In my lectures, I asked for a show of hands. In 25 years' time, how many of you will think you'll be living in the one-bedroom flat in Brunswick West? Ask for a show of hands. Most of the hands go up. Then I asked, how many think you'll be living in the 6-bedroom mansion in Toorak? This being the University of Melbourne, about 20% of the hands go up. So in other words, everybody has got a pretty good idea about how hard it is to earn money and what these two establishments are likely to cost. When I was talking to the Vice-Chancellor the other day, just as a joke, I said, I'm thinking of buying Malcolm Turnbull's spare Sydney waterfront mansion that he's got on the market at the moment. It's a snip at $18 million. He knows a professor of physics doesn't earn that sort of money. I was only joking, and he didn't go and audit the physics books actually afterwards to check if I was swindling them. But it's the same principle. This one-bedroom apartment, if you borrow the money at 8%, pay it off over 25 years, you've got to shell out about 5 cents every hour to service the mortgage. If you can bring in money at a faster rate than that, you can have that one-bedroom flat. If, on the other hand, you want to buy this mansion, you're going to need 4.4 million, and at the same interest rate over the same period of time, you're going to have to shell out 80 cents an hour. So if you can't bring in the money fast enough, that's where you'll end up. But if you're able to bring it in fast, you can have this one. And this is a metaphor for Western civilization. If you can spend the energy fast enough, joules per second or watts fast enough, you can have all the things that are on the left of my diagram. But if you can't spend the energy fast enough because you can't gather it quickly enough and burn it, then I'm afraid hunter-gathering is your destiny. Now, let me turn to the big picture. The 3 nearby planets, this one we're standing on and the 2 on either side. These 3 planets have, up until now, followed a destiny governed by the laws of physics. And on the middle planet, something new has entered the equation. The destiny of the middle planet will not be determined just by the laws of physics. Of course, everything is ultimately determined by the laws of physics, of course. But the middle planet's destiny will now be governed by the minds of men and women. Because the impact we're having on the middle planet is now equivalent to the geological forces that have shaped it up until now. The amount of stuff we move around the planet, the amount of transformation of the environment is now having an impact on a geological scale. And that's Janet's field, so I won't say any more. But let's look at these 3 planets in detail, because normally you don't do an experiment on yourself. You do an experiment on something else and see what happens to it. But we are doing an experiment on the middle planet right now. Let's see what the starting values are. If we look at the the temperature on the surface of each of these planets, we find that for Mars, the amount of heat that goes in equals the amount of heat that goes out, and the surface temperature is very similar to what you calculate theoretically. Here on Earth, the temperature of the Earth, if you do this simple calculation, should actually be on average 18 degrees below 0, and yet it's 15 degrees above 0. We'll come back to that discrepancy in a moment. Venus, even though it's a little bit closer to the sun than us, nevertheless reflects most of the heat back into space because of its clouds, should be 76 degrees below zero, yet is 460 degrees above zero. An incredible discrepancy. So we can't just calculate the temperature of these three planets just on the basis of the sunlight going in and the heat going out. There's something else going on. A clue is in the atmosphere. Both Mars and Venus have mostly carbon dioxide atmospheres in roughly the same proportion. Mars's atmosphere is very thin because the gravity is too weak to hang on to it, and over the geological ages most of us leaked out into space. Down here we see another big difference. Very little water vapour on Mars or Venus, but a substantial amount in the Earth's atmosphere. And Earth's atmosphere is predominantly nitrogen, not carbon dioxide like our neighbours. Let me digress for a moment and show you some holiday snaps. Here's me a couple of years ago giving an oration at the Roman amphitheatre in Orange in France, a magnificent construction made of stone. Here's another holiday snap. This is the Roman arena at Nîmes. And this is a clue to where our ancient atmosphere has gone. Because indeed, originally, Earth too had a dominant carbon dioxide atmosphere. But over 3.5 billion years, something strange happened on Earth. Life evolved. And the life ate the carbon dioxide out of the atmosphere and converted it into the stone that the Romans dug up and built these buildings out of. So this is the primordial atmosphere of the Earth turned to stone and put into the crust of the Earth. And that's why our planet has a different atmosphere to its neighbours. Now let's return to the calculation of what the temperature of our planet should be. The energy input to the Earth should equal the energy that's reflected back into space, plus the energy absorbed and re-radiated as heat. And at 12 noon, the sun delivers about 1,370 watts in every square metre of area, and the Earth reflects about 31% straight back into space. The albedo of the planet changes from over geological time. Now there's very little ice caps, but during ice ages when the Earth became increasingly covered with ice, you could get locked in by having an albedo of 99% and reflecting most of the heat back into space. Now, that's the first important thing. The second important thing is the rate at which energy is radiated away from an object that's warm. So those of you who like the odd bit of blacksmithing will be familiar with the annealing colours of iron. This is from a diagram from our mechanical workshop. When you heat anything up, it doesn't have to be iron, it could be copper, it could be nickel, it could be steel, it could be stone, it could be wood, charcoal. If it has these colours, then it will have the corresponding temperature. Now, the reason why an object starts glowing when it gets hot is because it's radiating energy back into the environment by virtue of its heat. And as it gets hotter, it radiates more energy. But this re-radiation goes not linearly, but as the fourth power of the temperature. The amount of energy radiated from a hot object goes as its temperature to the power 4. Now, when I present this in my undergraduate lectures, I hear, oh, what did he say? Temperature to the what? And I say, no, not temperature to the what, not temperature to the 1, not temperature to the 2, not even temperature to the 3, but temperature to the 4th power. Oh, right, is that going to be on the exam? Yeah, how's your Facebook page going? Yeah, right. No, listen. This is the scariest law in physics. Because what this means is you make a very small change to the temperature of an object, the amount of heat it gives off goes up prodigiously and disproportionately. This law was discovered by Stefan and his student, Ludwig Boltzmann. Boltzmann was a genius and developed a whole lot of very deep understanding of the laws of physics. More of that on this slide. This is his tomb in Vienna. He developed his most famous law, which is now engraved on his tomb. How important could a law of physics be that it's worth being engraved on your tombstone? This is the law of entropy, which we'll come back to in a moment. Meanwhile, back to the Stefan Boltzmann law. If this is the amount of heat diagrammatically radiated by an object at 500 degrees Celsius, this is the amount of heat for something only 190 degrees warmer. And this is the amount of heat for something that's only 2.5 times warmer. It's gone up disproportionately. The heat is just pouring off because of the Stefan-Boltzmann law. Another way of looking at this is if you take a poor person and shake them, not very much cash comes rolling out of their pockets, right? Because they're pretty cold in the cash department. But if you take a rich person and give Clive a good shake, cash comes pouring out of every pocket and checkbook and bank account, and even the Chinese kick in. Enormous amounts of cash comes pouring off because it goes as the fourth power of the amount of cash, or the temperature. So if we apply this law to these two objects, the sun, it's very hot, 5,780 Kelvin, about 5,500 Celsius. It emits energy at a prodigious rate, 63 megawatts per square metre. Whereas the Earth, with its average temperature of 17 degrees above zero, emits heat at a very leisurely rate, 400 watts per square metre. This is the rich guy, this is the poor guy. Now, let's apply that law to our own planet and see if we can fix the discrepancy from a few slides ago. This was first done by Svante Arrhenius, a Nobel laureate in chemistry, in 1896. He calculated what the energy balance was of our planet for the first time. He said, let's take the heat going in, let's look at the heat going out, calculate what the temperature of the planet should be, and he got the wrong answer. And he realised what he'd left out was the effect of the atmosphere. And he calculated the effect of the atmosphere and published it in 1896, and he said any doubling of the percentage of carbon dioxide in the air would raise the temperature by 4 degrees Celsius. Well, what's changed in 120 years? He got it wrong, it's about 4.5 degrees, we think. Nothing has changed. The laws of physics have not changed. Even the best supercomputer simulations still agree with Arrhenius' back-of-the-envelope calculation of 1896. Later he published this book, Worlds in the Making, where he recognised the sea was absorbing carbon dioxide out of the atmosphere, and he also figured that humans were changing the amount of carbon dioxide in the atmosphere by burning wood and coal in 1896, and he thought it would take humans 6,000 years to double the amount of carbon dioxide in the atmosphere at the rate they were going in 1896. Well, he was wrong. It's more like 200 years, and we're halfway there already. When he wrote this book and published it, appeared in English in 1908, he had a young postdoctoral fellow working with him, David Rivette, after whom one of our lecture theatres is named, who became the head of chemistry and later one of the founders of the CSIRO. So this Arrhenius influence still flows through the CSIRO today. So let's do Arrhenius' calculation. Here's the Earth absorbing sunlight. There's the solar input. There's some being reflected, the albedo times the input. And so the sun power in that's absorbed is 1 minus the albedo times the amount going in times the face of the Earth area that's facing the sun. But when the Earth re-radiates the heat back into space, it does so in all directions, just as I'm radiating heat forwards, upwards, sideways and backwards and downwards. And so the Earth's heat output is given by the Stefan-Boltzmann law for the temperature of the Earth times the total surface area of the Earth. And so simply by equating those two, cancelling off that stuff, putting in the numbers, we get the temperature of the Earth is 18 degrees below zero, which is wrong. The actual temperature of the Earth is actually 15 degrees above zero, and what we're missing is the greenhouse effect. In other words, standing here facing you in the lecture theatre, I'm not receiving any heat from the sun right now. Obviously it's night. And yet I'm still pleasantly warm. I'm receiving heat from the air in the lecture theatre, the floor, the walls, and even you radiating down towards me. So let us now consider where this extra heat comes from, the greenhouse effect. It turns out that any molecule in our atmosphere that's got 3 or more elements in it, 3 or more atoms in it, absorbs and re-radiates heat. The common ones, the nitrogen and the oxygen and the argon, don't participate in this effect because they don't absorb and re-radiate heat. Now, this is the composition of our atmosphere when I first downloaded this from Wikipedia a number of years ago. The most important greenhouse gas, that is to say the most important gas with 3 or more atoms in it, is water vapour, which has about 1% of the atmospheric composition. And it's responsible for about 30 degrees of global warming. But I don't need to bother about it further. I can focus in on carbon dioxide because the parochial misnaming of this planet by its dominant life form is just a disgrace. What's the biggest surface area of our planet? Is it Earth or is it ocean? It's ocean, obviously, and so we still call the planet Earth. We should call it ocean. And so the ocean dominates the contribution of water vapour to the atmosphere, and so far humans aren't changing that significantly. So that's a background of about 30 degrees we don't have to worry, well, do have to worry about it. But this one, on top of it, is changing. In 2009, this had already gone to 389 parts per million. Now, I have to say, the other subject I'm lecturing in first semester is advanced mechanics. And I'm still using the PowerPoint slides that Galileo used in 1630, because nothing has changed in advanced mechanics in 400 years. But this slide I have to update every year. 2009, 2010, 390, 2011, 393.7, 2012, 395.8, 2013, 397.2, and ladies and gentlemen, new world record in 2014, not one we should be proud of. We've just done 400 for the first time in 1 million years. What effect is this having on us? Well, here's my profit-loss balance sheet for energy, or more particularly power. This is the incoming radiation, on average 342 watts per square metre, averaged over 24 hours. This is what's reflected back into space, either from the atmosphere or from the ground, about 107 watts per square metre. But notice this one here, this arrow here goes straight into the atmosphere. Warning, your atmosphere is absorbing a component of the incoming radiation, causing the atmosphere to heat up. Then there's a bit of stuff to do with water being evaporated and raining. And then over here is the big one. The radiation coming out of the atmosphere and off the surface going out into space. Huge, 350 watts per square metre. This means that the atmosphere not only radiates out into space, but it also radiates back down to the surface of the Earth at a rate of 324 watts per square metre. Therefore, when I'm standing outside on a sunny day, I'm receiving 168 units direct from the sun, but 324 from the atmosphere. So the major source of heat is from the atmosphere, not directly from the sun, but indirectly through the atmosphere. Therefore, you should not do anything to raise the fraction of the energy absorbed by your atmosphere, because if you raise the temperature of your atmosphere, it'll have a disproportionate effect via the Stefan-Boltzmann law of the radiation that comes back down, which is already bigger than what's over here. And I never hear a climate change skeptic say, oh, yeah, I found an error in the Stefan-Boltzmann law. Ha, it's not t to the fourth, it's only t to the squared. Ha, it's all right. Never hear that. Strange. There's a little bit leaks out of the Earth from radioactive decay, naturally occurring radioactive decay, but it's a tiny fraction of what comes from the sun and of the atmosphere itself. That's the greenhouse effect. A further angle on the greenhouse effect is that the top of the atmosphere is where the radiation goes out into space. And when you fly, you'll observe on the in-flight display the temperature outside 10 kilometres above the Earth, where the atmosphere reaches space, it's extremely cold, maybe 50 degrees below zero. Whereas the bottom of the atmosphere where we live, it's 15 degrees above zero on average. Therefore, again by the Stefan-Boltzmann law, the heat has to be forced out of the atmosphere through this freezing cold 50 degree below zero layer. And so the radiation occurs very sluggishly because it's very cold. Whereas the bottom of the atmosphere is very hot, it's blasting down as the fourth power of the temperature. That's why a tiny change in the temperature of the atmosphere again has this disproportionate effect, because the heat has to go out through the cold atmosphere facing space. So let me turn now to climate change. We need some nuclear physics. Not all oxygen and therefore not all water is the same. Some water contains a light isotope of oxygen, some contains a heavy isotope, but it all tastes the same apparently. But we can tell that this heavy fraction of water, about 0.2%, can be used to measure the temperature of past Earths, because the heavy isotope of water evaporates more sluggishly because it's heavier, it falls out of the rain more readily, and consequently if we measure how much makes it to Antarctica, we can measure by a proxy the temperature of the atmosphere when that snow fell in Antarctica. And so going back 400,000 years, here's the oxygen-18 converted to a temperature, here's the carbon dioxide from the little air bubbles trapped in these ice cores, and just for good measure, there's volcanic ash every time there's a big transition. Somehow, volcanism is associated with big changes in the carbon dioxide of our Earth. Now, that's usually the end of the story. Oh, they're correlated. You know, it's very complicated. We don't know which came first. The carbon dioxide go up first, the temperature go up first, we don't know. In the same way, if you're in a car, the engine is very complicated. You don't know how it works, but you do know if you change the angle of the accelerator pedal, the car goes faster. So you could plot a graph, angle of accelerator pedal, speed of car, and that would give you a working idea, even though you don't know how the details of the engine works, apart from that it burns petrol and goes. So I've done the same thing with that data. I downloaded the original data set off the web. You won't see this anywhere else. I found 800,000 years worth of data, and I plotted it up. I ignored the year. I just took the CO2 level and the corresponding temperature from the oxygen-18 and made this scatter plot. So all these data points cover 800,000 years of information from the ice cores. And you see it all falls along this rough line. This is how the climate engine works. If you push this accelerator, you get that temperature. But there's one data point that doesn't fit. It's way out here, 400 parts per million. That's today. You see, our planet hasn't been in that configuration for 1 million years. So if the climate machine works the way it's done for the past 1 million years, we've pushed the pedal out to there. If the climate goes back onto the line, that's a 7-degree temperature increase. Almost certainly that won't happen because of feedback effects, but there's no reason to think this news is good. Finally, I just want to say something about the carbon isotopes in the air. Carbon comes in 3 flavours. They taste the same, but 3 different isotopes. There's the normal isotope, the common isotope, carbon-12. There's carbon-13, a heavier version, and there's carbon-14, which is produced by cosmic ray bombardment of the upper atmosphere, and is radioactive, decays in 5,730 years, the half-life. So, why are these important? Well, it turns out that nature, plants, growing things, prefer to eat up carbon dioxide containing the light isotope of carbon in preference to eating up carbon dioxide, the 1% that contains the heavier isotope. Therefore, if you measure a large volume of carbon dioxide, you can tell whether it came from a burnt plant or whether it came from some rock or something that didn't derive originally from life. And so this is now the change in the carbon dioxide as a function of time. From 1960 to 2010, measured on the summit of Mauna Loa in Hawaii. You can see it oscillates up and down each year. There's this annual cycle. What happens here is that the plants in the northern hemisphere, with the oncoming spring, gobble carbon dioxide out of the atmosphere and suck it down. Then the leaves turn brown and fall off and rot, and the carbon dioxide returns to the atmosphere. So this annual cycle is equivalent to 100 years of carbon dioxide emission from Australia, or 2 to 3 years worldwide. So in other words, if we wanted to arrest the background gradual climb in carbon dioxide, all we have to do is every 2 or 3 years harvest all the new growth on all the trees, bushes, plants, vegetation and animals in the entire northern hemisphere, put it in the ground and make sure it never comes out ever again. I don't think that's technically feasible. I don't think planting trees is going to arrest this relentless climb, because we're putting too much stuff for nature to take out in a short time. But if we turn now to the Australian Air Monitoring Station in Cape Grin in Tasmania, it sees the same carbon dioxide going up, and along with the carbon dioxide going up, CO2, the oxygen, is going down twice as fast. CO2. Somebody is burning carbon and sucking oxygen out of the air and converting it into carbon dioxide. We are. Don't worry, I forgot to explain last time I gave this lecture, there's plenty of oxygen in the air. The rate at this is going down. It's not going to cause shortness of breath anytime soon. Also, the amount of the heavy isotope of carbon in the atmosphere is going down, indicating that the carbon-13 isotope in the atmosphere is being diluted by an influx of the light isotope. Again, it must be therefore because of plants or plant matter, or something that was once a plant, is being burned. So we have no problem telling where the extra carbon dioxide has come from. It's come from burning plant matter. Oil, coal, wood, gas. Again, we see the nitrogen going down. Don't worry about volcanoes. Volcanoes cannot do this. So finally, the last part, a quick survey of energy and entropy. Australia only makes a small contribution to the total CO2 emissions, I hear people say, so we don't have to do anything. Good point, it's true that we only make a small contribution. And I checked, we have a population of about 23 million. Shanghai, the good people of Shanghai, about 13.5 million in the central few kilometres. They don't have to do anything either, because they're only a small fraction of the total. Greater New York, about 22 million, only a small fraction, they don't have to do anything. Los Angeles, only 9.8 million, don't worry about it, you just keep driving, you don't have to do anything. Pretty soon nobody has to do anything. This is the world electric power, dominated by coal, oil and gas, greenhouse emitting. A little bit of nuclear, a fair bit of hydro and some renewables. And the consumption is going up. Here's my third last question. You all showed me you understood my phone extremely well, or at least how much it cost in dollars. How much does it cost in joules? How many joules are there in the battery of my fully charged mobile phone? I've been going around the world insulting professors of physics with this question. The way a professor of physics responds to this question is to quickly pull out a pencil and an envelope and scribble furiously for 15 minutes and then give me an answer that's correct within about a factor of 10. Oh, this is a very well-educated audience. So the correct answer is indeed D, which I have an envelope here with the calculations on it if anyone wants to check it. But that's a very well-educated audience. In Queensland, they didn't do so well. Oh, I should have mentioned this. But I should point out that not all energy is useful. So here's my phone that needs 10,000 joules. Here's a bathtub full of hot water. If it's at a temperature of 60 degrees and cools to 20, it'll release 80 million joules into the environment. So I just have to have a cup of tea. And you might argue, therefore, that there's plenty of energy in that bathtub to charge 8,000 phones by conservation of energy, by the first law. Ooh, yeah, a nice hot cup of tea. Let me just check the temperature. I always like to use my pyrometer to check the temperature of the wall. 12 20 degrees according to this. 20 degrees. I'm just going to get my daughter to assist me. Could you just check the temperature of the lecturer? Just put the spot on my forehead and tell me what the temperature is, please. 35. Oh, I'm overheating. Okay, so let me check the temperature of my cup of tea. Ooh, it's a scorching 80 degrees. Let me just put that on there for the time being. Okay, but unfortunately, the conversion efficiency doesn't allow you to conserve energy here. In principle, you could suck the energy out of the bath and charge your phone, but it comes at an enormous cost. This gentleman, young man, died of typhoid, I think it was, tragically early, reflecting on the motive power of fire, calculated from the basic physics here that the maximum conversion efficiency here could only be 12%. And this now is the second law. So let me try and explain the second law in terms of dollars, because this was the equation that was engraved on the tomb of Boltzmann. One of the strangest equations in all of physics. Imagine you win the lottery, and the first prize is $7.69 million. And I present the prize to you as $1 coins distributed on every square kilometre of Australia. And here was the first one. I just found it on the doorstep when I came in. There's plenty more where that came from, young lady. Now, imagine she went to the coffee shop to buy a cappuccino and said, hey, I've got $1. I found another one. And there's plenty more where that came from. Please give me a cappuccino. The cappuccinos at the Potters cost $3.60. He's not going to give you a cappuccino. You need to have all the money assembled right there to exchange for the cappuccino. It's no good having it distributed all over the shop. This energy is not useful because it's not organised in a way that you can use. And unfortunately, nature always arranges the energy, or anything else for that matter, into a state that has the highest probability of existing. And you can imagine how many coin-sized patches there are covering the whole nation. And imagine how many different ways there are of inserting $1 into those coin-sized slots so they're a kilometre apart and there's 7.69 million of them. It's a mind-boggling number of possibilities. That's the number on the right-hand side of Boltzmann's equation, the W. And the left-hand side is the entropy. So this equation links a probabilistic assessment, the number of ways you can arrange the coins, with an amount of entropy, and the system always maximises S, the entropy. What you'd prefer is to have the coins arranged like that, all in one spot, but there's only one way of doing that. So that has a very tiny entropy compared to the other way, and that's the way you're going to find things most often. It's the law. I've just got 2 questions left for you. Can I ask now for another vote? How much energy is there in the tank of petrol in a Ford Falcon? We all got the price pretty much spot on. How much energy in a tank of petrol? This is a metaphor for Western civilization. Oh, well, it's early days yet, only 4 people have voted. Oh, this is a hard question. I've been insulting professors of physics all around the world as usual, and this time they take out a big piece of A4 paper, in fact a whole laboratory notebook, and they calculate for an hour and then give me a number that's out by 3 orders of magnitude usually. Okay, so 51 people voted, evenly distributed between A and D. That's not a bad effort. The correct answer is A. About 1 billion joules in a tank of petrol. 1 billion joules! Organised in the best and lowest possible entry configuration. So that when you twitch your right foot, that energy is on tap and can be burned at a furious rate to propel your car down the freeway at hundreds of kilowatts. Imagine more than 1,000 students pushing. No human in history has ever had that sort of power on tap. Tomorrow, I'm flying to Venice. When the A380 accelerates down the runway, it's burning the fuel at a rate of 60 megawatts. That's equivalent to 1 million students pushing my aeroplane down the runway to get it into the air. Don't take this for granted. This is what Western civilization costs. Whew. And you burn it. It's a fossil fuel. Okay, this is a Stirling heat engine, and that's operating just on the temperature difference, the 60-degree temperature difference between my cup of tea and the metal bin here, and it's been converted into kinetic energy. I could connect that to a generator and charge my phone, partially. These are the greenhouse costs of driving the Falcon, about 350 grams of carbon dioxide per kilometre. Think of it as a breadboard popping out of your exhaust pipe and dropping beside the road every kilometre. If you charge your car with electricity from the power point in Victoria, even a modest electric car will do about the same carbon dioxide because the electricity is derived from brown coal. The Tesla one does a little bit better, but you might as well just continue to burn petrol or diesel because the greenhouse effect in greenhouse emissions in Victoria will be less. Finally, if we're going to do something about meeting our targets, then we're going to have to get rid of this part of the diagram, the part that comes from coal and gas that emits greenhouse gases, and leave just the hydro, the wind and the solar. So as we go towards 2050, including cars, what are we going to do? Well, if we follow the lead of Germany, this is the German power demand in the summer of 1 week in the summer of 2012. There's a base load here in blue of hydro, then there's nuclear, brown coal, black coal, gas, wind and solar. You notice the solar and the wind go up and down. They're good during the day, but not so good at night. You need a backup. And if we're going to meet our targets, then we're going to have to get on with it. We're going to have to compensate for the not only the increase in demand, but by starting to turn the emissions down. We need to be more efficient. We need to put in more renewables. We need to capture carbon dioxide and store it. We need low CO2 sources. We have to be careful we don't do this, something that's going to take forever to have an impact. That would not serve us well. We have to be careful we don't do this, where something that costs an enormous amount of money but then doesn't deliver. These are terribly difficult decisions. And in our society, the level of debate is very poor in general. I haven't got time to go through all of these things, but you need to make sure you obey not only the first law, but also the second law. You need to look at the numbers and what your targets are, and whether you're going to get there with your favoured alternative. Don't confuse energy and power. You may have plenty of energy, but you can't burn it at a fast enough rate to buy Western civilization. Don't listen to this guy. And don't mix up military and civilian. I'll leave that. This is a very nice car I saw on the streets of Paris a couple of years ago. This car doesn't produce any greenhouse gases. It's charged from a power point. This is connected to a French nuclear power station. No CO2 emitted by this car. And finally, a few words about risk in making your decisions. How much should the dreadfulness factor guide your decisions? One final poll. Please look at these symbols and vote for the one that conjures up the most fear and dread in your mind. Put A if you're really worried about sharks or snakes. Put B if cigarette and other pollutants worry you. C if it's radiation, D if it's cars, or E if it's anything alcoholic. I'll certainly be getting stuck into one of those after the lecture. So let's see, what's the audience most afraid of? Well, that's very interesting. Okay, that's very interesting. That's a very well-educated audience, as I would expect from people who come to the July lectures. So, evenly divided between B and D. So what are the actual numbers? Cars, about 144 fatalities per million. Cigarettes, about 5,000, lung cancer. Sharks, don't even worry about it. Less than sharks. And I'm not sure about drinking, I couldn't find a good figure. Also, if you look at the number of fatalities that have come from various power stations around the world, this hydroelectricity is the worst. This failure in China, followed by coal and oil. So they're the ones we should be really afraid of. And we've got to keep it in mind that we do things differently here. So this Russian power station explosion killed 75 people and contaminated the river on which it was sited. Does this mean that hydroelectricity is too dangerous for Australia? After this accident, how many people even heard of this accident, by the way? A few. Were there people picketing to close the Snowy Mountain scheme? I didn't see any. When this Tupolev Tu-154 crashed in northern Russia and killed the Polish chief of staff, the president, and a few other people, does it mean we should ground our Boeings here in Australia? I don't think so. When the 3 Mile Island melted down, worst possible failure mode for a nuclear reactor, it blew radiation into the environment at a rate that was 1/150th of the total radiation that was emitted from American coal-fired power stations in the same year. Is this radiation different to what comes out of a coal station? It isn't. And Deepwater Horizon, terrible, terrible loss of life, 11 people killed, $20 billion spent so far to clean it up. Why are we doing that? And fusion may save us, but I wouldn't hold my breath. So finally, because time is short, Australia in 2050, my vision. I think we're going to need about 110 gigawatts of power. I reckon we can do tidal, hydro, coal and gas, wind, geothermal and solar, all the good renewables, at the following rates: half a gigawatt, 20 gigawatts, 4 gigawatts, 1 gigawatt and 10 gigawatts. That does not add up to 110, and I also haven't factored in cars, because we're going to take all the cars off the road as well, and we're going to need to replace them with electricity from somewhere. So in looking at the numbers, folks, I'm afraid the news is not good. The only way I can see that we can build an alternative that doesn't produce carbon dioxide in the time that has been set for us is the big nuclear. 65 gigawatts will be needed between now and 2050 if we're going to meet our targets. Only one country has ever done that on the time required, and that was France. Nobody else has rolled out any of these alternatives, even on the levels I've put up here, in the time that's available. We're also going to need a new sort of grid, because all of these things, cars being charged and discharged, sun going in and out, wind blowing and not blowing, tides ebbing and flowing, it's going to need to control enormous amounts of power at short notice all around the country. We're going to need a new grid control network. I have to leave it there. I have to fly. I'm going to give another public lecture on Monday morning in this lecture theatre. Those of you who recognise it will know this is the lecture theatre where Galileo gave his undergraduate lectures in mechanics that I mentioned a few minutes ago in the University of Padova. I have the privilege of giving the opening address at a conference there where I've been asked to give an update on my researches into Galileo's astronomical discoveries. So ladies and gentlemen, thank you very much for your attention. I'd like to end with Galileo's words, and I'd like to urge you, in making your decisions about the future, to consider some of the things I've mentioned here. And it's your decisions, and more particularly your children's decisions, I would say, from tonight's audience, that will shape the future of our planet. Make those decisions wisely. Thank you for your attention. I'm sorry, one final thing. I captured the CO2 that my laptop generated in making tonight's lecture into these Coke bottles. Actually, it was just one day's worth of preparation. It took me about a week to prepare this lecture. Could I please ask you to take a bottle each home with you tonight, and please put it somewhere where we never see the CO2 ever again, all right? It's not radioactive, unfortunately. It doesn't decay. You'll have to sequester it forever. There's enough here for everybody. Don't fight. There's plenty to go around. Thank you. Sorry, Jan. Sorry.
Well, how do we follow that? I'm sure David would be delighted to take a few questions if he's got the energy left. I'm sure he'd be delighted to take some questions. Can we start over one? Lady at the back. Yes.
Given that the Senate is about to repeal potentially the carbon tax, what would you say?
Actually, I was going to start this lecture by saying I'm a physicist and I don't want to get into the politics. I just want to give you the facts, and then the politicians, or we should vote for the politicians that we think are going to act on the facts in a sensible way. I was a bit shocked to see in the newspaper today that the Anglican Church Synod has urged our Prime Minister to respect the science. This is a church speaking, and I've got a picture of Galileo facing the Inquisition up on the screen. That's a good sign, I think. Look, I think a carbon trading scheme, providing everyone's in it, is a good start. I think closer to home, we should be urging our local MPs to do something about this. If we work for a big organisation like the University of Melbourne, for example, we should be urging the university to not invest in fossil fuels and start a tide. I say that because Stanford University has led the charge here. Last month, Stanford decided to get rid of all of its investments in the fossil fuel industry and set the leadership in that area. I think if it doesn't come from the universities, then we're going to be probably not going to get very far. But look, every opportunity you have to speak to those who govern us, I think would be a good thing to do. And also set a good example.
In the spirit of the quote, can we take $1 from every Labour and Liberal voter as they leave, and give us a country bottle, and possibly think of having next week's lecture without the heater on?
Yes, unfortunately we can't turn off Western civilization on this continent. We know that this continent will sustain a population sustainably, as it has done so for probably 40, maybe even 70,000 years without Western civilization, but it's probably not a lifestyle any of us would choose to adopt of our own volition. And now there are far too many of us on this continent. We have to rip drinking water out of the sea because we've now consumed all the rivers, but there's no going back, I'm afraid. There's no going back. And in the hot, crowded world of the future, we're going to need even more resources to manage our affairs. It's too late. We've gone down this pathway. This is our destiny. 7 billion people on a planet built for 500 million. We're going to have to think big, hard and fast.
The projection of 110 gigawatts, what it was, the power companies have got, at least in Victoria, have had a traditional 2% adding to 19 per year growth, which worked fine until 2007, 2008, but their business model was still going 2%, where in reality we're going down at 1.5%. So what's the margin of error on that 110, and does it take consideration?
Yeah, very good question. There is no margin of error. In fact, 110 assumes no growth between now and 2050. No growth in our consumption whatsoever, because I factored in our generating capacity, which is 45 gigawatts, and I've added our mobile capacity, cars, trucks, buses, aeroplanes, which is about 40 gigawatts. That gives you 95 gigawatts. I've assumed 110. So that, and if our population goes to 35 million, as I think some of the forecasts predict by 2050, that desalination plant is going to be nowhere near adequate.
Thank you, Professor. I will show because in the back. What solution you have for pollution and population? The reason I ask all these questions is that they are the subject interesting. Do you think how much science of the physics help us control the tsunami, control airport, and control other things?
Okay, well that's a big question. I'll just deal with the first one, the question of waste. One of the things that I'm struck with is that, of course, our present power stations generate an enormous amount of waste per unit of energy generated. In fact, I should have mentioned that here in Victoria, we have world leadership in this. No one generates carbon dioxide at a faster rate per unit of energy generated than we do in the state of Victoria. So you might expect, therefore, we should be at the pointy end of doing something about that. There's only a power station in eastern Germany, I think, that is worse than Hazelwood, and everything else is much better than Hazelwood, but that doesn't set a very good example. And the amount of waste is truly enormous. I was shocked to get my power bill on my very modest house, where I've got LEDs everywhere and I don't have air conditioning or a home theatre system or anything. I'm still producing several tonnes of CO2 per day, and yet I'm hardly doing anything. So if I had to deal with those several tonnes of CO2 each day and bury them in the backyard or something, it would be impossible. Now this is, obviously it's a AAA battery in our flat, but my family would consume about that much uranium in 70 years if we got our electricity from uranium. So in my view, having waste that stays in the power station has a tiny, tiny volume, and if the power station goes wrong, the people of Melbourne suffer, not the people of Bangladesh or the Pacific Islands, seems to me a very good deal. Here we take the responsibility for our own living the good life and don't inflict the downsides on someone else. And it's not hard to imagine you could stash that somewhere, even on your backyard, because it's, it's not a gas, it's not vaporising, it's a metal. Put a bit of concrete around it, bury it. I wouldn't do this, of course. Put it in a suitable repository. But the volumes are tiny, absolutely tiny. In fact, I had the pleasure of being at Lucas Heights one year when they were taking away the waste from the old high-F reactor. I'll finish the story in just a second. And they were taking it away on a ute. It was in a concrete steel cast. They put it on the back of the ute, and then there was a motorcade of like 50 vehicles, great big trucks full of soldiers or something, and clean-up teams, and they blocked all the roads in that part of Sydney, and they went down the docks and they took a few kilograms of stuff off to France for reprocessing. So that's only a very small reactor, and in fact the waste is then returned to Australia after reprocessing and sitting in a tank next to the director's office. So there's 50 years of waste from a 20 megawatt reactor sitting in this little pool, 5 metres away from where the director sits. So from my point of view, this doesn't seem like a big deal, but other people's opinions differ.
What's your thoughts about thorium reactors, and why do you think fusion hasn't got much of a chance?
Okay, so thorium first. If you Google Jamieson thorium, you might find the radio interview I did on thorium if you want a more nuanced answer. But the short answer is if you're going camping, going to the forest, going to the bush and you want to get a fire going, you wouldn't use all the green wood lying around. You'd gather up the dead wood because you can light a fire and away you go. You might be able to burn the green wood once the dead wood fire was going. Thorium is to uranium as green wood is to dry wood. Thorium is not fissionable. As it comes out of the ground. It has to be transmutated into uranium-233, which is a fissionable isotope, in an ordinary uranium reactor. So you can't start a nuclear power industry based on thorium. You have to start on uranium and then breed uranium-233 from the admittedly incredible abundance of thorium we have in this country, but we've also got an incredible abundance of uranium. There's no reason why you should go to thorium. India doesn't have uranium, it does have thorium. They're buying uranium for us, and they're going down the thorium path. It will take 40 years, probably, before they have enough thorium for a self-sustaining nuclear fuel cycle. Fusion. Fusion is a really, really, really hard problem. And It's been 20 years away for my entire life, as far as I can tell. I have visited the big fusion reactor in the UK, the Joint European Torus, when I was a postdoc in 1988, and I was confidently told, yep, we're just replacing all the carbon tiles with beryllium and then we'll break even, and then it's away we go. That was 1988, no more good news from there. They're building this big one in France. I'm not confident this will be ready in the amounts that we need to make a difference by 2050 at a cost we can afford. I'd like to hope there'll be a breakthrough, but people have been breaking their heads on this now since Hans Bethe solved the energy problem in the sun with the thermonuclear fusion. And of course we can't use the sun's fusion on Earth. It only works in a huge reactor as big as a star. We have to use a different sort of nuclear reaction, different fusion reaction here on Earth, and it hasn't been cracked. I have to say, from the first time the fissioning of the uranium, the fissionable isotope of uranium was discovered in 1930-odd, I think it was, by Fermi, the first chain reaction was underway about 15 years later. It's a much easier problem, fission. Fusion, very hard. We're not smart enough to solve that one.
I'm aware of the time, and I know there are a number of questions, so I might take one more, and then we'll call it quits. I actually think we should just be harnessing David. He seems to have enough energy to power us all.
We'll see what the blogs say in a minute. Yeah.
This is a related question for last one, but I'm assuming you're advocating your model for basically the whole world. And so what sort of technology are you talking about? You're talking about basically conventional reactors that are using 0.7 or so percent of uranium. You're talking about other reasons. You're talking about some future technologies that you imagine is possible.
Okay, it's a very good question. What sort of reactors am I advocating? I'm not advocating any reactor at all, actually. I'm just saying here are the numbers as I see them that could allow us to meet the 2050 deadline. Other people may have a different view. They may think we can roll out other clean technologies in that time scale on the magnitude that we require. And I would like to put up the nuclear option, because it's already been done by France in the time that's required and the magnitude that's required. So we do have a precedent for what works. French consumers, by the way, pay 10 cents a kilowatt hour for their electricity, and that includes a 10% levy, I'm sorry I have to say this, for waste disposal and power station decommissioning that goes into a trust fund. I think my 30 cents a kilowatt hour contains no such levy for waste disposal or power station decommissioning. Even if Australia decides not to go down the nuclear path, then perhaps we could use that scenario, that possible scenario, to evaluate alternative scenarios. Maybe we decide, okay, we'll leave nuclear alone because it's just too scary, or the economic conditions aren't right, and we'll do something else. But we'll keep our eyes open and say, okay, we're going to pay 60 cents a kilowatt hour, and we're doing that deliberately and with full knowledge of why we're doing that. So that's fine. If the citizenry decide to do that, well and good. But we should not put things to the side because we don't want to talk about them, or it's inconvenient, or for some reason too scary to consider. I have to acknowledge, though, that people don't always do things for sound, rational reasons. The dreadfulness factor is important. I had Sir Chris Llewellyn-Smith visit me a few years ago with his wife, and he was the director of the fusion project in France at the time. And he said, look, we want to go touring in the countryside, and Lady Veronica's a bit afraid of snakes. How will we know if we see a snake whether it's a dangerous one or not? I said, Chris, no problem. If you see a snake, it's a dangerous one. But for some reason, they're more worried about snakes than the Victorian drivers, which are far more dangerous. That's just, the dreadfulness factor. Sorry, that was a long answer to what should be.
I think on that note, we'll give David a break. So kindly agreed to hang around a little to answer some of the questions that we did get to. So if you still have a burning question you want to ask,
doing the honours.